Hi guys, today we're going to go over Chapter 5, Section 3 for Honors Chemistry, Periodic Properties of the Elements. Valence electrons are the electrons in the outermost energy level of an atom. You can find the number of valence electrons by looking at the group number, or the group number minus 10 on the periodic table. For example, if I go down to this periodic table down here, the group number is at the top, and that tells us how many valence electrons are in that group. Group 1 has 1 valence electron, so all of these alkali metals have 1 valence electron. Group 2, the alkaline earth metals, all have 2 valence electrons. We usually skip over these transition metals for honors chemistry. Don't worry about them yet. We can worry about them in AP Chem. Group 13 has 3 valence electrons, and then group 14 has 4. Group 15 has 5 valence electrons, 16 has 6. The halogens, group 17, have 7 valence electrons, and all the noble gases, except helium, have 8 valence electrons. Helium only holds 2 electrons, so it only has 2. So it's an exception in the 18 group. All right, the octet rule says that elements in the S and the P blocks are more stable, which means they have lower potential energy, so their energy goes down when all of the S and the P orbitals are filled. So here is my S block over here. Okay, so all of these are the S elements. That's our S block. It includes hydrogen and helium over here. And the P block is this section over here. This is our P block. P block. These are all filling up P orbitals. The S block is filling up the S orbitals. Let's make this darker. Okay, so the S block is the first 2 groups, and the P block is these 6 groups over here on the right. When all of these orbitals are filled, it has lower energy, and the ones that have a full octet are going to be these noble gases right here. So this little section, group 18, these have completely filled S and P orbitals, so they are more stable, they're lower in energy, and all the other elements in the S and the P block want to be like the noble gases. That's why they're noble. They're the snooty gases. Okay, the octet rule applies again only to the S and the P block. We don't worry about the D block. That would be this center one right here. We don't worry about the D block or the F block until AP Chemistry. Okay, so this F block and D block we will worry about later. The S and the P block want to have 8 electrons. Coulomb's law is the reasoning behind all of our trends that we're going to see below. So Coulomb's law says that the force, that's what F is K, which we will not worry about. So we're going to completely ignore K, times Q1. I'll write this over here. Q1 is a charge, okay, as is Q2. Q2 is a second charge. So any charged particle, it's usually a proton and an electron, but it does not have to be. Okay, R is going to be this distance between them. So R is the distance between those 2 charges, and then F, of course, is the force. Okay, when they're opposite, like I drew up here, the force is an attractive force, meaning it pulls them together. If I were talking about 2 electrons being near each other, that would be repulsion, so they would be going away from each other. Okay, so if Q1 and Q2 are opposite charges, plus times a minus will give us a negative force. The force is going to be negative, and that means it's attractive. If they are both negative, negative times negative is a positive, or if they're both positive, positive times positive is also a positive value. So if the force is positive, it's a repulsive force. For atomic radius, that's half the distance between the nuclei of identical atoms that are bonded together. So if I look down here, we have fluorine, this is F, chlorine, bromine, and iodine. And so when you put two of those atoms together, you can see that it's going to get bigger as we go. This is down a group. And the radius, we take it as half. So this is the radius. It's half of the distance between two identical atoms. Usually what we think about as the radius of the atom is the distance between the nucleus and the valence electrons. So that is going to be very similar to the technical definition of radius. Okay, so when I say it has a large radius, that means that it's a big atom. And if it has a small radius, like over here, that means that it's a little atom. Okay, we're going to look at the trends in atomic radius. So we're going to fill in the box below. And I would like you guys to answer right now. What happens as you go across a period? So as I'm going left to right across this period from lithium down to neon, can you see a general trend in the size of the atoms? Hopefully you can see that the atoms are going to get smaller as we go to the right. So the bigger atoms are on the left, the smaller atoms are on the right. And this is especially true if you look down here at group 4. So as you go to the right, the atoms get smaller and smaller and smaller. What happens to the radius as you go down a group of elements? Pick any group and go down, and what happens to the size of the atom? Okay, if you said that they get bigger, you are correct. The atoms get bigger as you go down. So let's talk about why. Now, the period trend is counterintuitive. It's a little confusing. Why should barium be smaller than cesium when barium has more protons and electrons in it? So if you have more protons and more electrons, why is it smaller than the one to the left of it? The answer is because in the case of cesium and barium, this is the 6s area right here of the periodic table. So cesium has 6s1 as its outer electron, and barium has 6s. It has 2 electrons out there, but they're both in the s orbital, and if I were to draw the atom with its 6 energy levels, 5 and 6, I should have picked a smaller atom, having 1 electron out here and having 2 electrons out here does not really affect the size. So what's affecting the size is the charge. With the greater charge, if I add just 1 more proton and just 1 more electron, they are more attracted to each other because of this equation up here, Coulomb's law. So what I did was I didn't really change the radius by adding an electron to the same energy level. What I changed was the number of charges, and a greater charge, positive and negative, is going to lead to a greater force. Okay, that greater force, as we move to the right, as we move left to right, the greater number, for example, fluorine has 17 positives and negatives. Boron only has 13 positives and negatives. So the greater nuclear charge pulls the electrons even closer. It has a greater force of attraction here. So as you go to the right, you're adding electrons to the same energy level. And for period 2, right here. For period 2, we're adding to the 2s and then the 2p energy level, and this is the second energy level. It's going to be the same distance from the nucleus. So we're not adding any energy levels. We're adding electrons to the same energy level 2. But what's increasing greatly is the nuclear charge, how many protons are in the nucleus. So let's sum that up. What we're going to say is that electrons are being added to the same energy level across a period. However, the greater number of protons in the nucleus, which we call the effective nuclear charge, that's how many positives are in the center, causes a greater Coulombic force. That's just a fancy way of saying force of attraction. So it causes a greater force, which pulls the electrons closer to the nucleus, and therefore the atoms get smaller as you go to the right. Now, going down a group, you guys said that it gets larger going down, and you're correct. Going down each group, the atoms get much bigger. If I compare francium down here to little lithium at the top, you can see it's much bigger. And the reason is, as you move down, every period that you move down on the periodic table, you're adding an entire energy level to the atom. So hydrogen and helium have 1 energy level. Lithium has 2 energy levels. And then if I go down, we're going to have 3 energy levels. So as you go down, you're adding a whole energy level to the atom, and that's why they get bigger going down the group. Let's answer these questions. Which atom is larger in each pair? And then we're going to put these 3 elements in order from smallest to largest. Okay, between nitrogen and neon, we're going to need to use the periodic table to look at where they're at. Nitrogen is right here, and neon is right here. What happens as you go to the right? We said they get smaller, so that means nitrogen should be a larger atom than neon. So which is larger? Nitrogen. For the second set, calcium or gallium? Calcium is here, and gallium is way over here. It's farther to the right. Calcium is closer to the left, therefore it's a bigger atom than gallium. Calcium is larger. And then we have sodium or potassium, Na or K. Which one is larger? Na is right here. K is right here. Which is the bigger atom? Well, potassium is down, so it's in the 4th period. It has 4 energy levels, and sodium only has 3. That means potassium is going to be larger. And last but not least, carbon or silicon. Carbon is right here. Carbon has, it's in the 2nd energy level. Silicon is in the 3rd energy level, so you add an energy level. So silicon is going to be the larger atom. Oops. All right, and then we need to find aluminum, sodium, and sulfur. Let's see where those are at. Aluminum is right here. Sodium is right here. And sulfur is right here. So we want to put them in order of increasing radius. So that means the smallest will be S, followed by aluminum, and then sodium is the biggest because it's the farthest to the left. Okay, so we said it was S is going to be the smallest, followed by aluminum, and sodium is the biggest. Okay, in terms of their radius. Okay, I have a silly symbol to help you guys remember the trends. If you understand the reasoning, you don't have to memorize them because you'll just use your brain to figure it out, but sometimes we need a little reminder. So as you go down a group, it's showing you that the smallest atoms are on the top and the biggest atoms are on the right. And as you go left to right, it's getting smaller. So the smallest atoms are on the top right, and actually helium is the smallest atom of them all. It's even smaller than hydrogen. Helium is the smallest, and the biggest atom would be the farthest to the left and the bottom, which is francium. Francium is largest, and this weird symbol almost looks like an R for radius, and that might help you remember the trends. So top right is going to be the smallest, bottom left is going to be the biggest for radius. All right, and most of the other trends are the opposite of that. So if you memorize radius, you can know what the ionization energy and electronegativity are.